Good day everyone. This video presentation is about coulometric titrator. For introduction, coulometry is an electrochemical method based on the quantitative oxidation or reduction of an analyte. It measures the amount of analyte by measuring the amount of current and time required to complete the reaction. In coulometry, the number of moles of electron that participate in a chemical reaction are measured. This is the example equation. This is the titration of chloride and ion. Then, silver electrode is used to produce silver cation. The titrant is generated electrochemically by a constant current from an electrolyte. It measures the silver cation in solution by the second electrode. It only gets a complete circuit when silver cation exists in the solution. It only occurs after all chloride and ion is consumed. By measuring the amount of current and time required to complete reaction, can determine the amount of chloride and ion. There are two types of coulometry. The first one is the control potential coulometry. Then the second one is the coulometric titration. The control potential coulometry is more selective than constant current coulometry. In a coulometric titration, the time needed for complete reaction measures the number of electrons consumed. The coulometric titration is an absolute determination technique in which the mass of a given substance is determined by measuring the quantity of electricity required to electrolyze the substance. It does not necessarily require a standard solution.
For the principle, during an electrolysis, the total charge Q in coulombs passing through the electrochemical cell is proportional to the absolute amount of analyte by Faraday's law. Q equals to NF NA, where N is the number of electrons per mole of analyte, F is Faraday's constant, 96,487 coulombs per mole, and Na is the moles of analyte. Thus, when the passing of constant current I, the total charge is Q equals to I times T, where T is the electrolysis time, and can be used to calculate the quantity of charge required to attain the end from the magnitude of the current and the time of its passage. Controlled current coulometry, also known as amperostatic coulometry or coulometric titrimetry, uses a constant current which passes through a cell until an indicator signals completion of the analytical reaction. The quantity of charge required to reach the endpoint is then calculated from the magnitude of the current and the time that current passes. When called coulometric titration, electrons serve as titrants. An example is the titration of halides by silver ions produce a silver anode. The current is coulometric titration is carefully maintained at a constant and accurately known level by means of amperostat. Controlled current coulometry has two advantages over controlled potential coulometry. First, using a constant current leads to more rapid analysis since the current does not decrease over time. Second, with a constant current, the total charge is simply the product of current and time. A method for integrating the current time curve, therefore, is not necessary. In controlled current coulometry, a constant current continues to flow even when the analyte has been completely oxidized or reduced. A suitable means of determining the endpoint of the reaction is needed. We can use the endpoint for redox titration, visual indicators, and potentiometric or conductometric measurements to signal the end of the controlled current coulometric analysis. Most of the endpoint detection methods applicable to volumetric analysis are equally satisfactory. Visual observations of color changes of indicators, as well as potentiometric, amperometric, and photometric measurements have all been used successfully. And for the instrumentation, controlled current coulometry normally is carried out using amperostat, an electrochemical cell consisting of a working electrode and a counter electrode. The working electrode is constructed from platinum, is also called the generator electrode since it's where the mediator reacts to generate the species reacting with the analyte. The counter electrode is isolated from the analytical solution by salt bridge or porous pit to prevent its electrolysis products from reacting with the analyte. So for the instrumentation, you can see a typical coulometric titration cell. It consists of generator electrode at which the reagent is formed and an auxiliary electrode to complete the circuit. The generator electrode, which should have a relatively large surface area, is often a rectangular strip or wire coil of platinum. A gauze electrode such as the cathode can also be used. The products formed at the second electrode frequently represent potential sources of interference. For example, the anodic generation of oxidizing agent is often accompanied by the evolution of hydrogen from the cathode. Unless this gas is allowed to escape from the solution, it is likely to react with the oxidizing agent. To eliminate this type of difficulty, the second electrode is isolated by a sintered disc or some other porous medium. An alternative to isolation of the auxiliary electrode is a device in which the reagent is generated externally. The apparatus is arranged so that the flow of the electrolyte continues briefly after the current is discontinued, thus flushing the residual reagent into the titration vessel. Shown is the cell for external generation of acid and bases. The apparatus shown provides either hydrogen or hydroxide ions depending on which arm is used. The cell has also been used to generate other reagents such as iodine produced by oxidation of iodide at the anode.
This is the setup of coulometric titration. In the coulometric method, the titration cell consists of two parts, an anodic and a cathodic compartment. These figures show both compartments separated by a ceramic diaphragm. The anodic compartment contains the analyzed solution, which includes sulfur dioxide, iodide, and imidazole needed in the chemical reaction. Methanol or ethanol is usually used as a solvent. The coulometric method measures water levels much lower than the volumetric method.
Calibration measurement. Coulometry is an electrochemical method in which the total charge or the total number of coulombs consumed in the redox conversion of an analyte at an electrode is measured. Coulometry is distinguished from voltammetric and amperometric methods by not relying on the mass transport current control to obtain a signal dependency on concentration. Coulometry is an absolute method, which means that calibration is generally not necessary as electrical charge can be measured with high accuracy.
For our maintenance and troubleshooting, we can maintain the quality or the correct result in a coulometric system by often changing the reagent. Kasi po, kapag hindi po na-change yung reagent, it can cause in the salt interference na nagkakos ng decrease sa transfer ng electrons. Which is, kapag hindi nga po nag-transfer yung electrons, dun po lalabas yung mga incorrect result and low recoveries of the coulometric titrator. So, and kapag ang i-test po natin ay solid na mga bagay or solid na sample, kailangan po natin siya i-pre-dissolving with the solvent na compatible po dun sa sample matrix ng solid sample. And gagawa na lang po tayo ng solvent blank analysis para po maback calculate yung sample results. Or pwede rin po natin gawin yung oven method, pero mas mahal at mas mahirap po yung gagawin doon. And that will help po na kapag ginawa yan, hindi po magkakaroon ng salt interference sa coulometric system. Dahil kung may salt interference po, magkakaroon ng low recoveries and enormous results. For cleaning the cell body, ang ipanglilinis lang po natin sa cell body ay water or solvent like methanol po. And we can dry it at oven later at 70 degrees Celsius lang po. And for generator cleaning po, we can clean the generator using methanol din po. But we cannot use water because it can cause high drips and exhaust the reagent sooner na nagre-result po ng erroneous result which is very incorrect nga po. And kapag may nakikita na po tayong blackening dun sa cathode and anode, pwede po natin siyang linisin ng nitric or chromosulfuric acid. And later, rinse na lang po natin ng methanol para wala pong matirang acid dun sa generator and cell. And para po sa pH and conductivity of the sample, para ma-maintain po natin yung tamang result, we should use a pH between 4 and 7. Yung mga pH values po na outside dun sa 4 and 7, pwede po siyang mag-react with iodine or alcohol na magkakos ng mga unwanted side reactions. Dun po lalabas yung mga incorrect results. And it can lower the conductivity. Dun po mahihirapan po tayo at maapektuhan po doon yung repeatability ng measurement. Kung gusto po natin dapat 3 pong pare-parehas, hindi po natin yung magagawa. Kaya need po talaga yung pH between 4 and 7. And magkakaroon po ng message doon na nakasulat na reagent low. Doon na po natin kailangang palitan yung reagent or i-refresh. For our troubleshooting, ito po yung mga pwede nating gawin if we encounter yung mga iba't ibang pangyayari habang nag-experiment po tayo. Kapag sobrang taas po yung drift, baka ang nangyari po is yung nagamit natin na desiccant is used na po siya. So, we can check to replace it and check for leaks kung saan po nakakapasok yung mga moisture in the air na papasok dun sa titration cell. Or, yung titration cell po is untight. Kung saan may mga nakakapasok din pong hangin dun sa may titration cell. Yung septum po niya, kailangan po siyang palitan. Lalo na po kung may mga nakikita na pong visible holes. Baka po meron po siyang leak po doon sa ground joints ng titration cell. Nagkakaroon din po siya ng mga side reactions kung saan po too high po yung water dahil po sa consumption ng iodine. And kapag gano'n na po yung nangyari, yung reagent po, need na po siyang i-change. Drift does not change or does not raise after the sample addition. Alam naman po natin na dapat pag nagdagdag po tayo ng sample, tataas po yung drift niya. If the drift stays at 1,000 microgram per minute at hindi po siya tumaas sa 1,5 microgram per minute, baka po yung nilagay po natin ay low water content. Dahil kapag low po yung water content, magiging low din po yung drift. So, pwede po tayong gumamit ng mga reagent na pasok po dun sa sample or pwede po tayong gumamit ng catholyte. For that, ang gagawin po natin na troubleshooting is pwede po nating palitan yung reagent, pwede po nating fill up or palitan yung catholyte, and i-check yung electrodes. Another problem is titrator titrates over. Makikita po natin na kapag yung titrator ay sobra po yung titrates niya is makikita po natin ang dark brown na color which is an excess iodine. Ibig sabihin po nun, kapag may excess iodine, yung nilagay po na reagent is unsuitable, defective, or madumi po yung indicator electrode. I-check po natin yung indicator electrode at linisin po natin yon. Yun po yung dapat nating gawin if the titrator titrates over. We can also check the 4mm connector. And another problem is, titration stops after input of sample weight. Kapag naglagay po tayo ng sample, tas tumigil po yung titration, ibig sabihin, kapag 0 milligrams pa din po siya, yung titration time is sobrang ikli po. We can add within the minimum time po yung sample, the minimum time of titration. Dapat dun po natin ilagay yung sample para maiwasan po natin yung ganong pangyayari. And we can check for the generator electrode. And for generator electrode po, pwede po natin i-check kung nagpo-function siya ng maayos. If wala po tayong makita o konti lang po yung makita nating gas and wala po tayong makitang dark brown clouds dun po, ibig sabihin po ay defective yung generator electrode or kailangan na po siyang palitan. Kasi dapat po may makikita po tayong brown cloud dun po sa electrode cell or electrode cable. And para naman po sa indicator electrode, if yung indicator electrode po is nagkakaroon po siya ng 1.5 microgram per minute or 0 microgram per minute na hindi naman po yun yung kailangan nating malaman, ibig sabihin baka meron po siyang short circuit kung saan defective na po and kailangan na po natin siyang palitan. And that's all for maintenance and troubleshooting of coulometric titrator.
Applications. Coulometry can be applied to less than 50 elements in inorganic compounds. It is also used in nuclear energy field for relatively interference-free determination of uranium and plutonium. Coulometry is also used in electrolytic determination and synthesis of organic compounds. It is also used in detection in liquid chromatography and determine all components in mixtures of 3-nitrotyrosine, guanosine, 5-hydroxyindole, diacetic acid, homovanillic acid, and serotonin. Detection of broad range of important electroactive compounds in biology and medicine can also be used in coulometry. Also, it is used in industrial hygiene analysis, analysis of steelwork materials, application of coulometry for total antioxidant capacity, determination of human blood.